Hello students, how are you doing? I'm your professor and I'm very concerned about all of you, about all the people in our community who have lost some of their houses or lives of family, and that is very, very unfortunate. I wish you can stay safe and I wish I can see you back. I really appreciate having you around, watching you every day, coming and learning and growing, and that's something that it's it's one of the most beautiful things in this campus. I hope I can see you here and we can have together like some lemonade together or something, around, get together and just tell each other like good things about all these things, like how we are strong, how we are keeping ourselves up, and how we are dealing with all the things around. Well, I wish you the best. I am planning to post some 15 minutes videos about some of the topics. So I'm going to start today with something about metric spaces. So let me recap about quickly what a metric space is and I will provide some examples. A metric space is a set and a function d, and the function satisfies these three conditions. The distance from a point to another one has to be greater than or equal to 0. In other words, the distance cannot be negative. Number 2, the distance from x to y is 0 if and only if x and y are the same point. In other words, the distance between a point and itself has to be 0. And if the distance between two items is 0, it's because the items are really the same item. Lastly is the condition for the distance from x to y is less than or equal than the distance from x to z plus the distance from that z to the other point y. And that's what we call the triangle inequality, okay? So we saw one example last time, but let me start from scratch. Example 1. Example 1. Actually, let me put it right here. Example 1. That is the usual metric. Usual metric in R to the K. The usual metric in R to the K starts like this. You have E, the universe, the Euclidean space, and the distance from x to y is, in this case, x equals x1, x2, up to xk, and y equals y1, y2, up to yk. In this case is x1 minus y1, so I subtract the first entries, and then I square that, plus I subtract the second entries, and I square them, plus blah blah blah, until I finish. I subtract the last entries, and I square the difference. When I finish doing all that, I'm going to take the square root of that. That's called the usual metric. And this is nothing but the regular Euclidean distance. So the distance from, for example, from 0, 0, 0 to 1, 2, 3, 1, 2, and 3. This is 3. That point right there, the distance from the origin 0, 0, 0 to 1, 2, 3, that point right here is nothing but subtract the first distance. I beg your pardon, not the first distance, the first entry, 1 minus 0, right? And square it, that's 1. Subtract the second from the second one, 2 minus 0 is 2, and square it, that's 4. Subtract this minus that, that's 3, square it, that's 9. The answer is 14, and then you take square root. That is the distance, right? square root of 14. That is the distance from 0, 0, 0 to 1, 2, 3. Right? That's called the Euclidean distance. Of course, when k equals 1, what happens when k equals 1? When k equals 1, what happens? You end up with the distance from x to y, from x1, y1, right? x1 to y1 is nothing but these terms do not exist, and you end up with the square root of x1 minus 1 minus y1 square. The square root, the square cancels out, leaving the absolute value of x1 minus y1. For example, what will be the distance between 3 and minus 4? The distance would be the absolute value of the difference, which is 7, right? 3 minus 4, which should be the absolute value of 7, which is 7. Correct? So this is the usual metric. It's very typical, it's very normal, that is why it's called the usual metric, right? So in this case, when k equals 1, our universe really becomes r to the 1, or r, the real numbers. What is the name of this class, Charlize? Real analysis, right? Very good. Excellent. We're going to work with example number 2. Example number 2 is as follows. We have the metric space consists of the universe to be the Euclidean space R2, or the Cartesian plane, you can call it. And if x equals x1 comma x2 and y equals y1 comma y2, the distance from x to y is going to be just x1 minus y1. In other words, look at this guy and this guy, subtract them and take the absolute value, plus take a look of the second guy and the other second guy, subtract them and take the absolute value. When you add those absolute values, we obtain this distance. This distance is called the cab driver distance. Acá called the Manhattan distance, or the Paris distance, or the Buenos Aires, or the Madrid, or Mexico City, or Chicago, you know, big cities where the cab drivers drive very crazily, like in all the big cities, right? And so, for example, in this metric, what would be the distance between -1, comma 1? What would be the distance between this point, -1, comma 1, and the point 2, 3, 4, comma 3? 4, comma 3. What would be the distance? This question is for Michael Correa. Alright, Michael Correa, what is the distance between these 2 points? Let's compute it. The distance between these 2 points and 4, comma 3 is equal to, you take a look of the first entries and subtract them. How much is 4 minus -1? 4 minus -1 is 5. Absolute value 5 plus absolute value of 3 minus 1. Look at the second entry and look at the second entry. 3 minus 1 is 2. So the answer is 7. That is the distance from here to here. So the way you do it is like this. First, if you are a driver, you drive this way, and then you drive this way. Like if you were a little car, this is you driving, so you have to drive this way, and then you have to drive this way. You cannot go like this. I know there are desperate people in the classroom, right? Who is a desperate person? No, you cannot go like this because you would crash with the buildings, right? Suppose that this is like a huge city, like it can be Moscow, or it can be whatever. Los Angeles maybe. So you cannot go like this because you're going to crash with the buildings. You don't want to do that. You want to go this way. Boom and boom. Of course, the reality of the situation, if you are here and this is your house and you want to take a cab and you tell the cab, take me to my house, the cab is not going to do that. What the cab is going to do, the cab is going to go like bam, 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 and then arrive to your house. Of course, because I want to charge you more money, right? All right, that's called the cab driver distance. Let me give you another example. That's example number 3. Example number 3, and that's called the drug dealer metric or distance. Someone told me about this distance. They call it like drug dealer for some reason, but it's something like this. E is R2, and the distance from X to Y, in where X equals X1, X2, and Y equals Y1, Y2, the distance is, you subtract the first entries, X1 minus Y1, then you subtract the other entries, X2 minus Y2, you take the absolute value, then you add them up. It's similar to wait a second. I'm sorry, I didn't mean that. I meant, I'm sorry, well, everyone has mistakes. It's the maximum of these two numbers. The maximum of these two numbers. The maximum between these two numbers. Okay? The maximum. For example, what would be the distance from 1, 2 all the way to 3, 9? What will be the distance? Well, the way you do it is take 1 minus 3. And how much is 1 minus 3? Negative 2. So the absolute value of negative 2. And then take 2 minus 9. 2 minus 9 is negative 7. Negative 7. Take the absolute value and take the maximum of those numbers. So the absolute value of negative 2 is 2. The absolute value of negative 7 is 7. So what is the largest between 2 and 7? What is the largest one? The bigger one? 7, right? 7. That'll be that. In an example, in a visual example, it works like this. 1, 2. This is you. Alright? Say that you are the police. You are the police. Okay? Police. Right here. 1, 2. And you want to catch a guy, a bad guy, a drug dealer that is in 3, 9. 1, 2, 3. Then 9 all the way up to here, like 9. 3, 9, right? This is a bad guy. A bad guy. Okay, a bad guy. Like this. Okay? A mean guy. Right? A bad guy. Because you're the police, the way it works is like you can walk like this. But if you are here, you can hardly identify the individual because you are far away. For example, how much is this distance from here to here? How far is 1 from 3? 2. Do you guys agree? So if you go here, it's going to be hard to identify because you are far away from the individual. However, if you walk this way, how much is this distance? 7. Right? If you walk this way, because you're going to be closer to the individual, at this point you are going to be able to identify the individual. So the individual, while you walk this way, the individual, this is like how far you are from the individual in terms of recognizing. You, if you go this way, you cannot identify the individual. You need to walk this way. So if you walk this way, you're going to be able to identify it. So that's how far you are in terms of identifying the individual. It's called the drug dealer metric, okay? All right, those are 3 examples. All right, now I'm going to allow you to kind of digest these things. We have example 1, the usual metric. Example 2, the cab driver. This is the usual, this is the usual metric, and this is the cab driver. The one that you travel like this and then you travel like that. And then here's the drug dealer metric. This is how far are you from this individual in terms of identifying the face of the individual. You say, Professor, that's not nice because you are claiming that the bad guys are men. Well, no, I mean, what's wrong with this girl dressing up as a man? So what's wrong with that, huh? I got you, all right? All right, there you go. So let me erase it. So we have seen metric spaces. We saw examples of metric spaces. And how do we connect this with topological spaces? So here it is, here is the deal. So these are metric spaces. And here is a topological space. How do we connect them? What is the relationship between a metric space and a topological space? I'm going to give you the secret, okay? Here you define balls. The ball of radius r, center at x, is the set of y's in the universe E, whose distance to x is less than the radius. That's the ball. So this is the point x, this is the radius r, and this stuff inside, that's the ball of radius r, center at this point x. Okay? X is the center of the ball. So once we have these balls in this metric space, so I'm going to define a family. I'm going to define a family which is unions of balls. And which balls? Any possible ball that you can think. How many union of how many balls? 5, 7, infinity, a countable amount, uncountable amount, it doesn't matter. So I'm going to call this family tau sub d. And this family, unions of balls, the radii change, the center change of each ball changes, so you have plenty of balls. Therefore, that family is going to be a topology. And that's the connection between a metric space and the topological space. So every metric space induces or generates or spans a topological space, not the other way around. You have a metric space, you can travel this way, but you cannot travel that way. It's false that any topological space comes from a metric space. So let me continue with the example. Say that we're working with the metric space R2, right? And the distance is the usual metric, okay? The usual metric. Well, in this case, I'm going to consider X to be the same universe and tau union of balls. For example, this union, this union, this set is an open set. Why? Because it's a union of balls. In these new topological spaces, these are going to be my open sets, unions of balls. So I'm going to ask you a question. Oh, by the way, these balls do not include the border, okay? Do not include the border. Why not? Why the balls do not include the border? Why not? Because I'm asking the distance to be strictly less than r. Less. If I say less than or equal, yes, it includes the ball. Includes the border. The border, that's what I meant. If you say less, that means no. It doesn't include the border. It doesn't include the border. Alright? So, that's why this doesn't include the border. Question for you. Question for you. This question is for how about Meilin? Alright? Meilin. Okay? So suppose that you have this guy without the border, okay? So the stuff inside, no border, no walls, like no border, okay? Okay? No border. Alright. Is this open? Yes or no? The question is, Melanie, is it open? Yes or no? You say, well, I don't know, Professor. That's what you're going to say. I don't know, Professor, but I'm telling you, the open sets are unions of balls. In other words, Melanie, I'm asking you, is this a union of balls? You would say, I don't see any ball, Professor. Oh, come on, wait a second. There are balls inside, look. Here is a ball. Right? That's a ball. Can you draw more balls so that this object is the union of balls? Yes, I'm going to draw a big one right here. Right? I'm going to draw another one right here. Of course, without the border. Remember, without the border, okay? More. A lot. Like continue. Keep going. A lot. Wow. Yes. I'm feeling it. Right? A lot of balls. Right? Keep going. Yes. Conclusion. It is a union of balls. Hence, it's open. Yippee! It's open! You see what I mean? Those are the open sets. So this metric space generates this topological space. You see what I mean? The metric space ED generates the topological space defined by the union of balls. Alright? So that's how you connect both worlds. And this finishes the first 15 minutes video. Okay? Awesome possum.